Good afternoon, everyone. I'm Kyle. Thank you for coming. I know there's a bit of a storm out there in this area, so a lot of people are wanting to go home early, but I appreciate you being able to make it to the talk. So we're talking, of course, about supply chain attacks, particularly in Terraform. If you're a DevOps infrastructure, a platform engineer, whatever you want to call it these days, you've probably worked with Terraform or at least familiar with it in some regard, as well as the Terraform Registry, which is used to store a lot of the open source community content that is used with Terraform frequently. And today we're going to talk a bit about supply chain attacks in general, and then do a live demo of how we can actually apply that to steal a bunch of credentials from Terraform users. A bit about my background: I studied at the Massachusetts Institute of Technology, where I completed my PhD in the Computer Science and Artificial Intelligence Lab, which looks like a Dr. Seuss building, but actually has some interesting stuff going on inside. And now I own and operate my own company called Invictin Labs in Ottawa, Canada. Beautiful place if you ever want to come visit. So looking into what a supply chain attack actually is. Really what it comes down to is when an attacker injects malicious code into a trusted third-party source, and the victim uses that third-party source without first verifying it. So that malicious code gets into their code or their system somehow. And this allows the attacker to have access to either the victim systems or the victim's users in the case of something that gets redistributed out to end users. And this can occur in both open and closed source projects, of course. And we're going to go over a couple examples of these to demonstrate the scale and impact that they've had in recent years. So one that you may have heard of is called the SolarWinds attack. It was pretty large. It was 18,000 customers affected, estimated number, which included a number of departments in the US government. And it was a very sophisticated attack that went on for several months before it was detected, which was one of the leading factors in how big of an impact it had. It was attributed to the Russian-backed APT, Advanced Persistent Threat 29 group. And it really was one of the first things that highlighted just how vulnerable our global supply chains are in terms of software to these kinds of cyber threats. So let's look at what actually happened in this attack to get an idea of how they work. So September 4th of 2019, the attackers were able to get access to the build system, which they called Orion. And they think they may have done that through a compromised Office 365 account. And over the next couple months, they managed to inject a tiny strip of code into the build, just as a proof of concept, so that then, as an end user, when they received a copy of that build, they could verify that their injected code was actually present. And this was just to prove that this would work in preparation for the primary attack. A couple months later, they injected the malicious code, which is termed Sunburst, and they injected it into the build through the Orion build system. And that was then distributed by SolarWinds to the end users. And that was roughly 18,000 different organizations and government departments that received that malicious code. And it wasn't until almost a year later that FireEye, which is now known as Mandiant, announced that that they had been hacked because they were using this software. So that was then traced back into the SolarWinds software as the source of that malicious code, and that was when it was revealed that this had been going on for almost a year at that point. And the way they did it was quite insidious. They managed to gain access to that build system, as I mentioned, and what they did is, because it was a multi-stage build pipeline, they'd let the first stage build a bunch of DLLs and compile them. And then in a later stage, it would rename that DLL to something temporary. They would write a new DLL with the same name that had all of that same code plus some extra malicious code. They would wait for the build system to bundle all that together into the distributed package, and then they would delete their malicious DLL and rename the original one back to its original name so that anyone looking at the output artifacts would see the original DLL with no malicious code in it. And then that all got distributed into a package that was signed by SolarWinds. So the malicious code was signed by the trusted distributor. A company called CrowdStrike, which you may have heard of recently, at the time was doing a lot of consulting and investigation into cyber incidents. And in the words of a pretty well-known security researcher, it was the craziest thing you'd ever seen. And the results were pretty significant. So a settlement of $26 million against SolarWinds, There were tens of millions of dollars on top of that in terms of cost to investigate and deal with the problem. The US Treasury, State, Energy, Homeland Security, a bunch of departments were all compromised, so the value of that information that was leaked is immeasurable. And then hundreds of private companies, including some very big names that you've heard of, right? Microsoft, Intel, Cisco, all affected by this. So even companies that in theory have a lot of engineers working on security managed to get breached by this. And of course, the Kremlin denies any involvement in this, which is a big shocker. How about another one, NotPetya? This was another possibly, supposedly, Russian attack that was targeting Ukraine in 2017, which may be the most destructive and costly attack in cyber in history so far. Over $10 billion in total damages estimated around the globe. And this one was a bit more traditional in how it worked. So there was a piece of accounting software that was widely used in Ukraine, and the update server for the software was compromised. So the software regularly reaches out to a known update server and checks if there's an update and pulls it and installs it if so. But the attackers managed to get access to this update server and inject malware into that update instead of the actual update. And then there were a couple known exploits at the time. So the first one was called Eternal Blue, and it allowed machines that were running, that were not patched yet, to for scripts to be run on them remotely. And then there was another exploit called Mimikatz, which allowed extracting passwords from memory on the machine. And when you combine these two, plus the malicious update, essentially they were able to remotely execute code on these machines that would get the passwords, and then they would use those passwords to access other machines that use the same passwords because they were like Active Directory accounts. And that meant that any machine in the system that was unpatched, they were able to get passwords from it and then use it on all the patched machines. So anywhere there was like an old machine that was out of date, but someone could still log into and the password was still there, was vulnerable. And that is how it exploded in terms of impact. Because after they did that and they had access to that machine, they would encrypt the master boot record, and now you have all of your data locked up. And they weren't even asking for ransom on this. It wasn't ransomware in the traditional sense. Encrypting your MBR is a great way to do ransomware, but the attackers here didn't care about money, they just cared about damage. And the cost of this was estimated at, like I said, about 10 billion US dollars, but possibly more importantly, it was used to cover up a bunch of other things that may have happened on those systems before they were encrypted, so that none of that activity could be traced. Now, the people who did this were probably quite aware of the impact that this would have and the global scale of it, but simply did not care, which gives you a bit of an idea of the people who are doing these things. Another one, this is my favorite, just the way the social engineering that went into it. So the first two were closed source systems, right? No one can really inspect that source code before it gets distributed out to the end user because it's not visible to the end user. This one was a bit different because this was a big open source project. So this is a compression library that is included in almost every Linux distribution. And it took about 3 years for this attack to take place because there was the malicious version was eventually almost distributed. So it was built into development releases, and then this was detected before it actually went out into an official release, but it became very close. And if that had actually happened, the impact would be immeasurable. And the way it worked is it used the SSH daemon to grant system access to some external user because there's this commonly used patch that links SSHD with systemd, and then systemd includes lib ZMA, which is the XZ Utils library. So it was kind of this multi-stage thing that made it hard to trace how these packages were connected. But it was very close to being released in both Debian and Red Hat. And it was discovered only by chance when someone was using a development release of Linux, and they were like, why are there performance issues? And then they started investigating what was consuming these resources and found this malicious code in there and sounded the alarm on it and then prevented it from being released out into a production build. So the way it occurred was more through social engineering than anything else, plus some very clever programming. So there was a user, Gia T75, a pseudonym for someone, again assumed possibly connected to app29. They contributed meaningfully, so they did like real code updates, real pull requests, comments, reviews, like very useful work on this repository for about 2 years. And this allowed them to get the trust of the maintainers of that repository because they seemed to be doing real work. And then over time, there were a bunch of new users who popped up on the email list who started pressuring the maintainers saying, hey, you're not contributing enough time anymore, like it's time for someone else to take the reins. What about this person who's been doing all this great work in the last few years? Of course, these users were likely just alternative accounts of that same person. So the maintainers eventually granted this person maintainer status, which allowed them to change the build system. And in the build system, what they did is because it's a compression library, there are these binary files with different characteristics that are used to test the compression and make sure it's compressing and decompressing properly. And what they did is, while that's usually just random binary data, they created a binary test file that actually included malicious code in it. And when it was built and then released into the Linux systems, it would get the malicious code out of those testing binaries and build it into the library that is actually executed. This didn't have that much of an impact because it never really got released out into the world other than in development builds, but it made it through quite a few people looking at this code and no one noticing any of these in an open source project. So this supply chain attack issue is an increasing threat. It's not new, but it is getting worse over time. About 203 dependencies on average for most projects, according to some surveys. And about 45% of the respondents of the survey who had, 45% of them had experienced a supply chain attack in the year the survey was done. And almost 60% of them had no way to respond to it. They had no plan for what to do when this happened. So it impacts a lot of people and no one knows what to do about it. And that's kind of the problem. But I want to give you an example to really illustrate how big of an issue it is. So I went on PyPy at the Python package manager repository place to look at what is the most commonly downloaded package in the system. And it's Boto 3. If you've worked with AWS, you probably recognize that. That's Amazon's SDK for Python. And it has 142 contributors, 757 closed PRs, and 1.3 billion downloads in the past month alone. And it has a bunch of dependencies. Each of those has 50 to 100 contributors. Each of those have dependencies, and just one of those has all these dependencies. And so you can see how this tree starts to grow very quickly. And across this, you have about 2,700 contributors, almost 15,000 pull requests that have been closed and merged in. And then you have some really interesting information here. This package, I could not find who the author of this was. This package has one person who did it. We have no idea who that is. Certainly not vetted code that's going in there. And yet this is somehow making it into the most popular package on all of PyPy that is used for Amazon Web Services deployments around the world. So when you think of the sensitive information that this has access to and that this one person can inject some code into their package for, you get an idea of the scale and just how difficult it is to be able to catch this. We have the question of, okay, is it better to use open source or closed source to be able to deal with these things? It's a mix. There is no clear answer. On one hand, in an open source project, anyone can contribute to it, and there's very rarely any vetting of the people who have control over the build systems and such. Whereas in a closed source system, in theory, the company that's doing that has better control over that. But in a closed source project, the end user cannot review the code if they want to, in most cases, and there are fewer people looking at it to catch if that kind of malicious attack happens. In both cases, you can have inexperienced developers who are doing things that are not secure, but one of the larger issues with open source is that you don't really have much control over your dependencies because all the projects you're using, even if you're forking them and locking down the versions yourself, internally they're probably using other dependencies and you'd have to have this nested recursive forking of everything, and in the end you'd end up with, like that Boto 3 thing I showed you, hundreds of packages that you're trying to maintain yourself. So with that, now I will show you what actually happens here. Now, can I just get a show of hands in the room here who uses Terraform on a regular basis? If you're in this talk, I assume it's probably many of you. Okay. Okay, so I'm going to start by cloning a sample repository. Oh, I thought I changed it. Yes, okay. So I just cloned this repository. It's public demo. And if we look at what's in here, sorry? Make the text larger, possibly. Better? Okay, why is that happening? Something's going on here. Okay, so in here I have two subdirectories. One is the attacker, one's the victim. We are the victim today, so let's look at what's going on in here. A very simple configuration. NDC often has a Microsoft focus, so we're playing with Azure today. All this is doing, very simple configuration. We're using the Azure AD provider, an official Microsoft provider. We are setting up a provider for it with a tenant that I've created for this demo. And all we're doing is we're reading the config, and we are doing a check here that is comparing the tenant ID that the data source is getting with the one we expect, and saying, hey, yes, we are applying this to the correct tenant, and if not, it throws this error message. Now this module here, this is the assertion module, is one that I published myself a couple years ago. And if we look at it, this has 51,000 downloads this week, almost 5 million in overall time. And this is something that I, as an individual, published. Nobody knew my name. Nobody knows who I am. 5 million people have downloaded it, or it's been downloaded 5 million times by probably thousands. I would estimate with this number that there's probably 500 to 1,000 decent-sized companies using this module. And what I've done is I have forked it and republished it under a different user, so it's not linked to my account, called Please Don't Ban Me. And, oh, sorry, not that one. This one. Okay. Now what I'm going to do is show you this module. It's very simple. All it does is asserts that a condition is true, and if it's not true, it kills Terraform and fails with an error message, which is something that for some reason is still not built into Terraform, so I built a module to do it. It's much simpler now than it was when I first released it, because they've since added these validations with the ability to reference other variables. But essentially, it's just making sure that the condition is true, and if not, it throws that error message. Very simple module, nothing crazy going on here, nothing external, etc. So what I'm going to do is I'm going to publish this on the Terraform registry as version 0.1.4. And on the registry, when we refresh, we'll see, okay, that's our current latest version. Now, as I'm doing this, as the victim side of things, if anyone thinks, hey, that's crazy, that would never actually happen in real life, please call me out on it so we can talk about it. Because my assertion here is that this is very realistic. So we're going to move into this directory. We're going to start with a Terraform init. over the hotel Wi-Fi, and a Terraform plan. Okay, no problems here. The assertion passes because I am connected to the right tenant and everyone's happy. So now what I'm going to do is, as the attacker, I'm going to go in here. I'm going to delete this version. Remember, the attacker has full control over the publication of this module. I'm going to delete the release, delete the tag. And I'm going to publish a new release with the same version number. But this time, instead of targeting the main branch, I'm going to target the malicious branch. Publish that. Refresh this. Note that this showed up. That's interesting. But anyway, we're going to go back here. Now, okay, for this attack to work, two conditions have to be true. One, the Terraform directory, or wherever it's being run, has to be clean. So that could be, usually that's going to be because an engineer is installing it or cloning it onto a new machine, or a new engineer is doing it, or if you're using a pipeline, that's going to be a clean directory every time you run it, right? If you're using Terraform Cloud, that's going to be a clean directory every time. So that condition, I think, is very realistic that that would happen. Here, in this case, we're going to be simulating that just by deleting it, recloning it. The other condition is that you either have to wait 1 week, or you have to do a Terraform version bump. Anyone guess why that might be? No clever individuals out there? No. Okay, it's all right. The reason for that is because the Terraform registry uses Amazon AWS CloudFront, which has a 1-week cache timer on it. If we look at, okay, so I deleted that repository. I'm going to reclone it here. Great. If we look at the code here, so this is the Terraform source code, and this is where it gets, it finds modules. So module location function, and this is basically doing an HTTP request to try to download the module. And the reason that we can get around this 1-week cache timer with a version bump is because there's a header here for X Terraform version. So if we change the value of that header by upgrading from 1.10.4 to 1.10.5 in this case, then all of a sudden it has a new header and it bypasses the cache. Alternatively, we just wait for the cache to expire and we don't need to do the version bump. So we're going to upgrade from 1.4 to 1.5. Sorry, 10.4 to 10.5. Go back to our directory. And we're going to do our Terraform init again. No one stopped me so far, so I assume no one has any red flags here. So we've done our Terraform init. We'll do a plan. We're not going to do an apply, just a plan, just to see if there's any changes. No changes. Everyone's happy. And with that, the attack is complete. If we go into our victim's Terraform configuration here, and we open up Terraform, we open up modules, and we open up assertion, and we look through here, we see that all of a sudden we have all these extra files. Assertion, these are shell scripts, PowerShell scripts, interesting stuff. Because I'm running on a Windows machine, it's running the PowerShell script, so let's look at this. And this is doing some interesting things. So first it's starting this whole process as like a separate process. So it's starting a new process and running this, and then immediately returning to Terraform. And that way Terraform thinks it's done, even though now there's a new process running in the background. And what we're doing here is we're getting all of our environment variables first. because often Terraform is run with the client secret as an envar, especially if you're doing it in a pipeline. And we're putting all those in the payload, and then we're getting all of our files. Oh, here we're saying, is the Azure command line interface installed? If so, get the currently logged in, or the token for the currently logged in user. If the AWS CLI is installed, do the same thing. Get tokens for any profile that's currently logged in. And sorry, the one thing I missed here, this is too small for me, is we're getting files. There we go. We're getting all of our files from the .ssh directory, which is obviously going to include some sensitive stuff, private keys perhaps. We put all this in a payload, and now there's a couple ways that companies can try to stop an attack like this. And one of the most common ones is you lock down your network access, right? You ensure that even if an attacker can get into your system, you prevent someone from remotely accessing it to actively do things, or you prevent data from being egressed out of your environment into the real world, usually through whitelisting of domains of where things are allowed to connect to. And so I thought to myself, if it's a whitelisted system, and we're trying to do an Azure configuration here, what would be whitelisted? And what I realized is that that Azure uses the same domain for everything to log into any tenant. So when you try to log in, I try to log in, we use the same domain, which means that domain is almost guaranteed to be whitelisted, because without it, the AZ CLI doesn't work, Terraform doesn't work, nothing works with the Azure provider. So that is pretty much guaranteed to be whitelisted. So what I did is I created my own Azure tenant, and I make a client for it in Entra and a user in Entra, and then I make login requests against that. And what you can do, it turns out, is you can change. You can't really modify any of those and have it still work, but you can change, sorry for flipping around here so much, the user agent header. And you can put a nice little payload in there. And okay, maybe another way to stop this issue is deep packet inspection. Well, and look for anything that might be sensitive. Well, I can encrypt my payload using a public-private key pair, and now even if you can see that, what is that user agent field, you have no idea what I'm trying to egress. You just know that I'm trying to egress something. Anyway, I do a bunch of these. I split it into packets the right size, do a couple attempts for each because Azure is unreliable with its logging, and then exit it silently out of this script. This is public if you want to take a look at this and how it works. So now if we go into Azure, this is the attacker's tenant. And we can see we have monitoring down here. And we have this sign-in logs feature. And that timestamp seems to match up. Does it? No, it doesn't. This is where things get annoying, because this is a very unreliable feature of Azure's. Anyone here from Azure? You can't actually do that. You have to start over, and you have to put the end time in first. Yeah, no, someone's not a very good UI engineer. You also can't just leave this one blank and say until current date. You have to put a time in there. I'm always nervous when I do this demo because I'm relying on Azure to log things properly. There it is. Okay. So I have 3 failed attempts here. And now I'm going to download these. Download. And here things get interesting again because 1 kilobyte file, that's not right. Okay, let's refresh. because even though the logs propagate and show up here, when you download, they still haven't propagated yet there. Nope. Okay. Oh, our logs disappeared. Not very good for audit logs. I prefer to do this demo with AWS, by the way. 41 kilobytes. Okay, good. There we go. So now we're going to go into our attackers repository here and run our little Python script. So if we look at what I'm doing now, so this is from the attacker's perspective, essentially I am getting that log file that I just downloaded, and I am reassembling the packets, and then I am decrypting it, and then I'm decoding it, and basically getting all the raw data that I had. And I'm stashing it all in this retrieved directory here. And now we can see all the environment variables that were set for that user, and we've reproduced all of the files that were in .ssh. Huh, kidding, not a real private key. But that file was in the victims.ssh directory and had the proper permissions set on it. So now my attacker has all this information. And what I find even more fun is what I've done at the end here. Remember how I said I used that Azure command line to get the currently logged in token? Well, what I've done is I've gotten that token out of the payload, and then I've made an API request using that token to validate it. And it has succeeded. And what we see here is the output of that command. So using that token, I was able to get this response that shows the tenant ID, the domains that are associated with it, a bunch of other stuff. Now that token could theoretically do anything, right? Now that I have it, I can do anything I want, because usually when someone's running Terraform, they're using an admin level credential, because you need an admin level credential to do a lot of things with Terraform, like deploying your core networks and infrastructure. And this token will have all those permissions. So this concludes the demo and shows just how easy it is to conduct a supply chain attack. So now I ask you, I showed you that I have that module published with 51,000 downloads per week. If I actually did this, not on my demo repository, but on the real one, how many of your companies might have their credentials exposed? Because even if you're not using that module directly, you might be using one of my 50 other modules that use that module internally, or someone else's module that uses that module internally. So I encourage you to take a look into this and figure out if it's actually an issue for you. Now, something else that's interesting here that I was actually fairly impressed with, because someone yesterday said, well, what about using a security tool like Chekhov to see if there are any vulnerabilities before you do your apply? So let's actually do that. Going back to our file, our victims configuration here. It's only 4 files. I don't know why it takes so long. So while that's thinking, I'm going to show you. So the problem here is that the Terraform registry allows the underlying commit hash associated with a version tag to change. And that has been raised quite a few times. It was first raised here. Well, this particular issue was raised in 2021. One that references it and first talks about this problem is from 2018. I've raised it on the forums, I've raised it all over the place, and they just don't want to deal with it. I don't know why, but if you read through these conversations, it's quite funny, because it's like the head in the sand completely ignore that this is a problem. There we go. So This failed with Chekhov because it says ensure Terraform modules use a commit hash. And if you open this link, which is here, this is a known problem. Interestingly, this came up shortly after I first presented this demo, so maybe someone was in the room and then made this a policy check. But it does detect that there's a security vulnerability here. But then I thought, well, how is that actually happening, and how can I get around it? And what I realized is that if you have a module such as this one here, so this is a module I wrote just this morning to basically do what we were trying to do in that configuration. It validates, is the tenant that we are currently deploying to a tenant that we expect? Simple, unrealistic you'd actually use it, but basically it's doing what we just did, except it's wrapped it in a module. So it gets your current tenant, it compares it with an input tenant ID, and does this. And to please Chekhov, I am going to use this module using a hash. So you don't have to use the Terraform registry. You can use a GitHub directly, and you can specify the commit hash that you want to use here. Comment that one out. Initialize. And we'll run Chekhov again. And this time it passes, right? It's happy because now I have pinned it to a commit specific hash. But as I just showed you, if you go to this and you look at the code that is associated with that hash, well, it's using a module that's just using the Terraform registry. And the same attack would occur here because this underlying code would change even though the commit hash of the parent module hasn't changed. So Chekhov isn't going to save you in this case, unless they modify it to recursively go through all modules and make sure that everything has a pinned commit. But realistically, then you're not going to be able to use most of the open source modules. So there were a couple key objectives here. One, that the user was never alerted to this attack. They had no idea that this happened. It did not require admin access, admin consent or sudo. The user didn't need to provide any kind of consent at all, right? They just did normal actions like Terraform init and Terraform plan. And I took all of their credentials. We talked about how Chekhov isn't going to save you. And this, so I was rather concerned about this because I work with a lot of companies that I build Terraform configurations for. So I was like, there should probably be a CVE for this. So I wrote to HashiCorp and I said, here are all the steps for reproduce. Here's the risk. Here's the issue. Da, 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 da. And they responded saying, thanks, we'll look back into it. We'll look into it and get back to you. That was 7 months ago. They have not gotten back to me. And they refused to issue a CVE. And if you look at the CVE process, if you've done it before, if the program partner, which is HashiCorp in this case, refuses to issue one, there will never be one. There is no way to get around that, at least as far as I'm aware. Because that's step 2 right there. Report it to the partner, and the partner assigns the CVE identifier. They said no, so there is no CVE. It's a problem. Really, you just need to write to HashiCorp and say, this is insane, please fix this. But let's talk more about supply chain attacks in general again, because it's a problem well beyond just Terraform. So when we talk about reducing the risk of something, risk is the factor of probability and impact. And so we can reduce the risk by reducing the probability or reducing the impact. We can reduce the probability by a number of ways. The first one is if you have important dependencies, you can fork them, keep your own copy of them so they'll never change, and use those. Obviously, that gets extremely difficult when you have these nested dependencies and you'd have to fork each one and then change the references, and it's a whole thing. You can avoid dependencies altogether if you don't need them. In many cases, there's a lot of old code that has old dependencies in there that is no longer used. And strong dependency locking is key. Some languages have this built in for everything, which is great. Terraform has it for providers, but does not have a locking file for modules. And that is actually published on their website. We will lock providers, but not modules. No explanation why. And then you can prefer trusted vendors, but as we showed, closed source products are just as vulnerable to supply chain attacks, so that's not really going to save you. That one's questionable. On the side of reducing the impact, Well, we try to minimize the blast radius and try to minimize the impact that they can have. So we always want to use the principle of least privilege, right? Giving as the minimal permissions needed to a given credential to do what it needs to do. In this case, if I'm able to steal your Azure token, you'll want it to be as locked down as possible, right? So when your software is installed, you want to run it as a dedicated user with strictly limited permissions, not as root, okay? And yeah, for cloud tools, we want to go with role-based authentication as much as we can, so that it is limited to a specific role with very specific tasks, and very strict policies for being able to assume those roles. Wherever possible, keep it all read-only and not write access. Now, this used to be quite difficult with these cloud providers, particularly with AWS with their thousands of different permissions, but this has gotten a lot easier now with modern tools that will allow you to see, hey, your user or role has only used these permissions in the last few months. Check these ones and see, are they actually necessary? And AWS will do that now. I'm not as familiar with Azure, but those tools are present and easier to use. Network segmentation is fairly important. When you think about that XZ Utils library attack that allowed someone remote access into your system, if you can keep that network segmented as tightly as possible, so even if they can get into that machine, they can't branch out from there and then expand the blast radius, that's pretty important. So using multiple different subnets, particularly when it comes to cloud providers or different VPCs, using your security groups properly, access control lists, making sure everything's on the right ports, and restricting your outbound public access to make it harder to egress data. As I showed, you're never really going to be able to truly lock that down because there are ways to egress data through endpoints that I don't control, like Azure's login endpoint, but it certainly helps. And then we come to the monitoring side of things. Lots of tools, a bunch of companies out there and all around that are advertising the capabilities to do this. Monitoring your network traffic, particularly your logins. Why is Joe logging in at midnight when we know he's sleeping, right? Like, and you can flag some things and catch them pretty easily that way. Auto updates, huge risk here, as we talked about, when the update server can get compromised, like that NotPetya attack. So things automatically installing software without anyone's consent are pretty risky. When you do see weird behavior, actually digging into it. The only way that XZ Utils attack was caught was because one very keen user was like, that doesn't seem right, and started digging deeply into it. And that is when they found, hey, yeah, there's some weird code here that's using a lot of resources that it shouldn't be. So we can do that with performance. If you're looking at your network logs and you're seeing DNS requests for things that aren't recognized or new or abnormal, lots of machine learning tools able to monitor that now, or different software that's been installed that you don't recognize. Multi-factor authentication has been harped on for like the last 10 years, still just as important, still so few people are using it, because if malware can get on your system, they can steal your passwords, they can steal that out of memory, but they can't steal your hardware keys unless they are actually physically present to take your hardware keys. So hardware for multi-factor authentication, very useful for very high security systems. When we're talking about Terraform specifically, the Terraform Registry, we're still going to want to use all those third-party community modules. You can fork the ones that are very important, like you can do with any dependency, or you can pin it to a hash. And this is kind of what I showed you there to get to make Chekhov happy, right? So when we have the source, I think GitHub, Bitbucket, Mercurial, a bunch of them, any Git-based system, those will all support this ref with a hash. And when you do that, it's impossible to change the hash of a commit without changing, or to change the code without changing the hash. The problem here is that whatever you're locking to or pinning to might internally use modules that do not use this system, right? Like I demonstrated with that wrapper module. Alternatively, you can use something I built specifically for this. It is a module that does a module lock file. So this is open source. Feel free to take a look at it. But essentially the first time a Terraform plan is done, it looks for any new modules. It puts their it calculates a hash of all the files, puts that into a lock file, and then the next time it's run, it checks, is this already in the lock file? Has it changed? Then throw an alert. And it's fairly robust from my testing, but I'd love to see some more eyes on it if you're interested. And yeah, that's everything. Cool. All right, thank you very much for your time. Happy to take questions on this and talk about what we can do to deal with it.
It's probably a silly question, and I don't know Terraform, but why did you replace the 0.14 version instead of just making a 15 version?
Okay. Question was, why did I replace an existing version instead of changing the version? So if I change the version, if we look at how this was before I messed with it, if I do a new 1.5 version, then, so a lot of modules would do something like this, right? And in HashiCorp's language, this means that it's pinning the first two, and then the least significant version is allowed to change, right? So this would allow 0.1.5, 0.1.6, etc. If it's written this way, and I release it as a new version, then yes. The next time they do a Terraform init upgrade or a fresh init, then the malicious code will come in. But if they have it like this, then if I release it as a new version, then they're not going to get it until they bump the version in the config. And one of my objectives with the demo was to say the user doesn't have to do anything to be attacked. So that is why I released it as a new version instead of, or sorry, as an existing version instead of a new one. Yeah. Any other questions? Okay, thank you.